Okay, so let's talk about the differences between polar and nonpolar molecules. Now, to figure this out, first, you have to know how to do Lewis structures of molecules. So please refer to Lewis structures before you do this video. So over here on the left, I have several different types of molecules, and we're going to figure out if these are polar and nonpolar molecules. Okay, so the first one is NH3. So let's do the Lewis structure of NH3. Again, you should be looking at how to do Lewis structures before this video, but the Lewis structure for NH3 is this. So it's a single bond nitrogen hydrogen bonds, and the nitrogen will have a lone pair of electrons around it. So this is the Lewis structure of NH3, which is ammonia. Now, also, you should know from the Lewis structure to predict the molecular geometry. The molecular geometry of this molecule is trigonal pyramidal, and it is from the tetrahedral family. So, tetrahedral family, and it is a trigonal pyramidal. So looking at this, then, you can look at this in a three-dimensional way now. Trigonal pyramidal has the lone pair of electrons here, and I will draw it out like this. The dashed line means that it is behind the plane of the screen. The wedged line means it is coming up from the screen to you. So hopefully this will tell you what this looks like in a three-dimensional way. So looking at now the three-dimensional geometry of NH3, we can see that it has a lone pair of electrons here, which obviously is a very negative region in space because it is a naked lone pair of electrons. So that means that the rest of the molecule over here, these guys down here, are relatively in the positive region in space. So again, negative and positive designations mean relative to each other. Again, since there is a naked pair of electrons, it is a negative region, and that means that the other region in space is a positive region. Being that there is a bias of a negative region in space, there is more electron density that way than this way. Since there is a bias towards this as the negative region, we know that this is a polar molecule. So polarity means that there is a asymmetrical, a non-symmetrical distribution of electron density around a molecule. Whereas in a nonpolar molecule, which we'll see later, there is a symmetrical or even distribution of electron density around the molecule. So let's look at the next molecule, which is CH4. And again, the Lewis structure for CH4 is this, and this is then a tetrahedral. Molecular geometry, and if I was going to write it out to help you see. Okay, so with these bonds are in the plane of the screen. The dashed line bonds are away from the screen or perpendicular to the screen, and the wedged is perpendicular to the screen and towards you. So, as you can see, there is an even distribution of electron density because every single one of these carbon-hydrogen bonds has the same degree of polarization, meaning that, again, think of your electron negativity. That's very important here in designating polar and nonpolar bonds. But electron negativity tells you the carbon is more electron negative than hydrogen, so the carbon atom is pulling the same degree amount of electron density to itself. And because these are all hydrogens, they all share the same pull. That means that the overall density around this molecule is exactly the same. They're all pulling towards the carbon in an even way. So this molecule then is polar because there is a symmetrical distribution of electron density. So CH4 is nonpolar. Okay, looking to the next molecule, PCl5. So PCl5, phosphorus pentachloride. If we draw the little structure of this is phosphorus, obviously has chlorine this way. If I was going to write out actually draw out the molecular geometry, you would have to know that the chlorines are in a plane like this, and above and below the phosphorus is the other chlorides. So this is a trigonal bipyramidal molecular geometry. And because, again, all the electron negativity, the polar bonds in the PCl are all exactly the same magnitude, we know that chlorine is more electron negative than phosphorus, so the chlorines around the phosphorus are pulling the electrons towards it in the same exact degree, which makes the total electron distribution around here, around the phosphorus, exactly the same. So this is a nonpolar molecule. And just to make it a little bit more clear, if I change one of the chlorines, and let's change one of the chlorines into, let's say, a bromine is less electronegative than chlorine, so that means that its arrow is less. Okay? That makes it a non-symmetrical distribution around the molecule. That means that there is more electron density going to the chlorine than to the bromide. So that means that, relatively speaking, this bromide is now positive in nature, and the region in space where the chlorines are is more negative. This then would give us a polar molecule. For PCl4Br. Okay? Let's look at the next one. Okay, so the next molecule is PCl3. PCl3 is very much like the same molecular geometry as NH3. This is the molecular geometry, the Lewis structure of PCl3. The molecular geometry is trigonal pyramidal. And now you know that because of the lone pair electrons here, this is the negative region in space. Everything else then has the more positive relative to that naked lone pair of electrons. So now that we know that we have a biased distribution of electron density, then this is a polar molecule. Okay, looking at the next one, nitrogen monoxide. Let's draw the Lewis structure for that. Okay, so this is the Lewis structure for nitrogen monoxide. So as you can see, oxygen is more electron negative than nitrogen, so the electron density is now towards the oxygen because this has more electron negativity. So because oxygen has more electron negativity than nitrogen, so this is a polar molecule because there is a bias of electron density that way. So this is polar. Okay, looking at the next one, carbon disulfide. The Lewis structure for carbon disulfide is this. Between carbon and sulfur, sulfur is more electronegative than carbon, so the electron density in this bond, in this double bond, is towards the sulfur. For this bond here, it's also towards the sulfur. But because the pull is exactly the same, because these are both sulfur molecules, sulfur atoms, then the dipole moments negate each other, so you have a net zero dipole. So because of that, it shows that the electron density is exactly evenly distributed in the molecule because of the same magnitude of electron negativity of the sulfur to the carbon. So this is going to be a non-polar molecule. Again, if I changed that one of the sulfurs to an oxygen, then we changed the relative polarity of the molecule, because then we know that oxygen is more polar than sulfur. I mean, oxygen has more electron negativity than sulfur, so it will pull the electrons towards it more than the sulfur. So now we have a biased distribution of electron density, so that means that this is now a polar molecule. Okay, so here we have NCS. This is a theoretical molecule. It doesn't actually exist in nature, but I just figured that teachers like to put these types of molecules on tests. So anyway, there are two valid Lewis structures to this molecule as written. Just looking again, asking whether these two structures are polar or nonpolar. Well, again, polarity deals with the even distribution or non-even distribution of electron density. And because sulfur and nitrogen have different electron negativities, so we can say that sulfur is more electron negativity than nitrogen. So its pull of electrons will be stronger than this pull of electrons here. Same thing down here. So in either structure, sulfur is pulling more electrons towards it. That creates a biased atmosphere of electron density. So we have a more negative region here in space. So this is more negative then. And that means that this area here is the more positive region. So since there is a asymmetrical or a non-symmetrical distribution of electron density, then this molecule is going to be a polar compound.